Alright, this is the second introductory video on chemical equilibrium. We're going to look at a few more introductory level problems. This can be used for review or as a way to introduce yourself to some of the simple problem solving in the unit. This first question illustrates a topic that I don't think we've talked about in class yet. We're told that the value of Kp for this reaction, this is the Haber process for producing ammonia gas from nitrogen and hydrogen. It's very small, 4.51 times 10 to the minus 5 is the Kp value at 450 degrees. For each mixture below, we want to just decide, is the reaction at equilibrium or not, and if not, indicate the direction that the reaction proceeds to reach equilibrium. If you think you know how to do this, just jump in and try it, pause the video, and then see if you're right. So what we want to do for each of these questions is calculate the value of the reaction quotient. You remember that the reaction quotient has the symbol Q, and its calculation is done in the same way as the equilibrium expression. So for this reaction, nitrogen, hydrogen, and ammonia, we'll write the expression Q equals, and since we're dealing with pressures, we'll say partial pressure of ammonia, the product, squared, because its coefficient is a 2, divided by the pressure of nitrogen times the pressure of hydrogen cubed. So there's the value of Q, the reaction quotient. Now let's calculate it. So for part A, the pressure of the ammonia is 98 atmospheres, and we're supposed to use atmospheres when calculating Kp, so that's good. We don't have to convert units. So 98 squared divided by, and now I'll leave out the units here because I'll be lazy, 45 times 55 cubed. So grabbing a calculator, we get 98 squared divide by 45 and divide by 55 cubed equals 1.3 times 10 to the minus 3. Now what can we learn by looking at that value for Q? Well, the first thing we notice is that Q is not the same as Kp. Kp up above was 4.51 times 10 to the minus 5. So since Q is not equal to Kp, the obvious conclusion then is that the system is not at equilibrium. Okay, if Q is equal to Kp, then yes, the system was at equilibrium, but here Q and K are different, so this system with those pressures of ammonia, nitrogen, hydrogen could not be an equilibrium system. But can we now conclude the direction that the reaction will go? So for example, will we shift in the forward direction? If we do, we're going to cause the pressure of nitrogen and hydrogen to decrease, hydrogen to decrease, while increasing the pressure of ammonia. Or will we shift in the reverse direction, which will cause the pressure of ammonia to drop and the pressure of nitrogen and hydrogen to increase? So what direction will this reaction shift in order to reach equilibrium? Well, when you look at the expression here, we realize that our value of Q is larger than Kp. So Q is larger than Kp in this question. Therefore, Q must decrease. Okay, the equilibrium constant is constant at a given temperature, so it's not going to change, but Q can change as the reaction shifts. Now, how can you make a fraction get smaller? We want this fraction to decrease. Well, a fraction gets smaller if its numerator decreases. If we decrease the numerator, or if the denominator increases. If you make the denominator larger, then Q will get smaller. If you make the numerator smaller, then Q will also decrease. Now, if you're decreasing the pressure of the ammonia and increasing the pressure of nitrogen and hydrogen, can you see what direction this reaction must have been shifting? So decreasing the ammonia and increasing the nitrogen and hydrogen, well, that's a reverse shift. Okay, a reverse shift. So we could say here, therefore, the reaction shifts backwards. Now, you don't have to go through that reasoning every single time. There's a fast way to reason this out, and it just involves a little bit of memorizing. Whenever Q is equal to K, like we see here, then the reaction is at equilibrium and there's no shift that's going to occur. If Q is greater than K, like we just saw here, then the same logic will apply. The numerator will have to decrease, and those are your products. The denominator will have to increase. Those are your reactants. So if you're losing products and getting more reactants, whenever Q is bigger than K, the reaction shifts backwards. Similarly, if Q were less than K, then the reaction would shift forwards for the opposite reasons. So if you just memorize those three situations, that when Q is equal to K, you're at equilibrium. Q is greater than K, you'll shift backwards. And if Q is less than K, you shift forwards. Now logically, if you think about it, you really only need to memorize one of those two latter situations, and everything else should fall into place. Alright, let's quickly do part B and C. Same logic. Q, I'm not going to rewrite my expression since I just did it above. Q is equal to the pressure of ammonia, so 57 squared over 143 times, and now I realize I should have read that faster, right? Because there is no hydrogen. If there's no hydrogen, then this is a very simple question. You can't be at equilibrium unless all three things are present, right? So if there's no hydrogen, then you can't have a forward reaction, right? You need nitrogen, you need hydrogen to shift forwards. Since hydrogen is missing, the reaction must shift backwards to reach equilibrium. Now, I suppose we could sort of use a mathematical approach here and say, you know, if we put a 0 in here, we have a problem because we're going to be dividing by 0. But if we think about what happens as the hydrogen pressure gets closer and closer and closer to 0, then we can see that Q is going to get larger and larger and larger. So essentially, this Q is going to become infinitely large as the pressure of the hydrogen gets closer and closer to 0, which means we can use the same sort of logic here as well, that Q will be much larger than K, and then Q must decrease. But probably better would be our original reasoning, without hydrogen in the system, so no hydrogen, go back down here, no hydrogen, not at equilibrium. So you must make more hydrogen to reach equilibrium. At equilibrium, everything in the reaction has to be present. You need both a forward and reverse reaction to be occurring at equilibrium. So we need to make more hydrogen, which means a reverse shift. Okay. Part C, this one has all three things present again, 13 atmospheres of ammonia, 27 nitrogen, 82 hydrogen. So if we plug those values in, all three of them, we get Q equals 13 squared over 27 atmospheres times 82 cubed. Be sure you're plugging things into the right places in your expression. So 13 squared, divide by 27, and divide by 82 cubed, and we get 1.13 times 10 to the minus 5. And now when we compare that to the original value for K, which was 4.51 times 10 to the minus 5, we see now that Q is less than K. So Q is less than K, therefore we get a forward shift to reach equilibrium. It's not currently at equilibrium. The reaction will shift forwards to reach equilibrium. So there's a new concept for you to decide if a system is at equilibrium. Calculate Q and compare it to K. If they're not equal, it's not at equilibrium, and if Q is larger than K, you get a backwards shift to reach equilibrium. If Q is less than K, you get a forward shift to reach equilibrium. Alright, this next question is a more standard, straightforward equilibrium problem. We're given a reaction of CO2 decomposing to make CO and oxygen. Everything is gas phase, so this is a homogeneous gas phase reaction. The chemist put 10 grams, and I notice grams right there. That's a little annoying. I'll have to convert that to moles, and then with the volume in a 2-liter vessel, we'll find concentrations. At equilibrium, she discovered this many moles, so that's moles. We don't have to convert to moles for CO, so this is CO in the vessel. What's the value for Kc? Now, since we were told what was placed in the vessel and then what is at equilibrium, this is a signal to set up an ice table for the reaction, since there's a starting set of conditions given, and we're going to need the equilibrium set to find Kc. So let's write the equation. 2CO2, everything's gas, so I'm just going to leave out the phases here, produces 2 COs and O2. In a heterogeneous reaction where there are solids and liquids present, I would put the phases in, because then we have to pay attention. Solids and liquids are not part of the equilibrium expression, right? So the initial, the change, the equilibrium, that's our ice table. And so I'm going to go off to the side and just do a quick little conversion. You can use formulas or unit multipliers to convert your 10 grams of carbon dioxide in a 2-liter vessel. We're going to need that in molarity. If you prefer formulas, then use 2 little formulas. Moles is mass divided by the molar mass, and concentration is moles divided by the volume. Volume in liters, right? Or we can use unit multipliers, and I'll just do that real quick here. We have 10.0 grams of CO2, 1 multiplier, get rid of grams, switch to moles. The other multiplier, let's divide by volume. So I'll just leave 1 on top, and I'll put liters on the bottom. So now I've got grams canceling, and I've got moles over liters. This is going to be molarity. Okay? So the molar mass of CO2 from a periodic table, 1 mole weighs 44.01 grams. Our volume was 2.00 liters. So now, with a calculator again, we have 10 grams divided by 44.01 and divide by 2. And if you compare what I'm doing with unit multipliers to what you would have done with formulas, you'll realize you're doing the same thing, right? Mass divided by molar mass is 10 over 44.01, and then dividing that by the volume gives you molarity. So with 3 significant digits, looking at those numbers, we'll get 0.114 as our initial concentration of CO2. So that was the only thing placed into the vessel. So 0.114 is my initial concentration of CO2. Nothing was placed in for CO or oxygen, so I'm going to put zeros beside those two. Now at equilibrium, there were 0.020 moles of CO. So converting that to a molarity, so we'll divide that by the volume, and we'll get 0.0100 molarity of CO at equilibrium. So that's on the equilibrium line of my ice table. So I just used my little C equals N over V formula for that. So now we're going to fill in this ice table, and so we look at the CO column where we know 2 of 3 numbers right now. We started with nothing and we ended with 0.01, so clearly we must have increased by 0.0100. Since we've increased the CO, we'll increase the O2 as well. They're on the same side of the equation. and we must be decreasing the CO2 because it's on the opposite side of the equation. So this reaction was shifting in the forward direction, right? So now looking at the ratios, 2 to 2 to 1, we can fill in the rest of the change line. That's the line of the ice table which is dependent only on the ratios in the balanced equation, the stoichiometry. So since the CO2 and the CO have the same coefficients, this guy will lose the same amount, so 0.0100. And the oxygen has a 1 as a coefficient, so 1 to 2, it's going to gain only half as much, so 0.00500. Now at equilibrium, what have we got? If you started with 0.114 of CO2 and you lost 0.01, you're going to have 0.104 molarity CO2. For oxygen, you started with nothing and you gained this, so you're going to have 0.005 molarity oxygen. Now that I've got everything at equilibrium in concentrations, we can go set up the Kc expression and substitute to find its value. So products first, concentration of CO squared, because its coefficient was a 2, times oxygen's concentration to the power of 1, its coefficient was 1, divide by the concentration of CO2 squared. And now plugging our numbers in, we get 0.0100 squared, 0.005, and 0.104 squared. So the Kc value, grabbing a calculator now, trying to pay some attention to sig figs, 0.01 squared times 0.005 divided by 0.104 squared. I guess we'll keep 3 significant digits, so we get 4.62 times 10 to the minus 5 is the value of Kc for this reaction. Notice that it makes sense that the Kc is small because very little of our CO2 reacted. Right? We started with 0.114 and we only lost 0.01. So since you're not losing much of your reactants here, your Kc value is going to be less than 1. If you were losing about half of the reactants, then Kc would be close to 1. And if you were losing most of your reactants, then Kc would be much larger than 1. We could even calculate, if we want, the percent of CO2 reacted. We don't have to do this, it's not asked for, but let's just jump in and do it. Since the percent reacted will be the amount that reacted, so 0.0100, this is the amount that reacted from the CO2, divide by the starting amount. Okay, don't memorize this, hopefully you just make sense, it's logical, right? What percentage reacted? Well, I'll take the amount that reacted, and I'll divide by what I began with. Then I'll multiply by 100 to get percent. So 0.01 divided by 0.114 times 100, only about 8.77% of the CO2 decomposed. Since so little decomposed, the Kc value is small. Okay? The next question, again, you can pause the video whenever you like and try them on your own, right, rather than just watching. You've got 4 moles of SO2, 1.5 moles of oxygen in a 5-liter vessel. As soon as I see that, I'm thinking moles divided by liters to get molarity. And it was allowed to reach equilibrium here, so SO2 and oxygen make SO3. And at equilibrium, there were this many moles, and so the moles there will have to be converted to molarity as well, of oxygen in the flask. What's the value of Kc? So this is very similar to the one we just did. We have initial conditions up here. We have an equilibrium condition down here. So there's the need for an ice table. 2 SO2s. This is all gas phase, so everything is going to be included. So I'm just going to rewrite the equation and fill in my ice table. The initial, the change, the equilibrium. So initially, and I'm using my little C equals N over V, concentration is moles divided by the volume in liters. So 4 moles divided by 5 liters will be 4 divided by 5, 0.800 molarity for the SO2. 1.5 divided by 5 is going to be 0.300 molarity for oxygen. There was no SO3 placed in the container, so it starts off at 0. At equilibrium, 0.715 was the moles of oxygen remaining, so 0.715 divided by 5, 0.715 divided by 5, 0.143 molarity is the remaining oxygen at equilibrium, so I'll put it under oxygen on the equilibrium line. Now, looking at the oxygen column where there's two numbers known, we can figure out the missing number. If you started with 0.3 and you finished with 0.143, how much did you lose, right? You had to lose to get there. And so the SO2 will be losing and the SO3 will be gaining. Of course, another way to figure out what's losing and gaining is that there was no SO3 initially. If there's no SO3 initially, this reaction could not have gone backwards. It has to be going in the forward direction to make more SO3. To reach equilibrium, the forward and reverse rates will have to be equal. Initially, there's no product, so the reverse rate would start at 0 in this question. So now, if we take 0.3 and subtract 0.143, we get 0.157. That's the amount that the oxygen lost. And now the change line can be filled in. Once we know one of the things on that line, we can fill in everything else, and that's based on the stoichiometry. So 2 to 1 and 2 to 1, the other two are going to lose and gain the same amounts, twice as much as the oxygen. So multiplying that by 2, this guy loses 0.314 molarity, and this guy gains the same amount. And that's again because of the 2 to 1 ratios, they'll lose and gain twice as much as the oxygen. So for the SO2, if you began with 0.8 and you lost 0.314, you've got 0.486 molarity left. And for the SO3, you began with nothing and you gained 0.314, so you've got 0.314 molarity at equilibrium. Now I've got everything in concentrations at equilibrium. It's easy to calculate Kc. We'll write the expression, concentration of SO3, the product, squared, divided by concentration of SO2 squared times the concentration of oxygen. Your coefficients in the equation become the exponents in your expression for Kc. Products go on the top, reactants go on the bottom for Kc. So we get 0.314 squared over 0.486 squared and 0.143. So Kc will equal, grabbing a calculator now, 0.314 squared divided by 0.486 squared and also divided by 0.143, and I get Kc is 2.92. Okay? When Kc is close to 1, and this is close to 1, we know that the reaction is going to be about 50% complete, give or take some, right? And we can see that that was true here. You had a 0.8 originally, and you lost 0.314, so it's close to 50% complete. Okay, that logic is a little bit of a simplification because it ignores the coefficients, which become exponents, and it ignores there's two reactants and only one product. But as a general rule, when Kc is close to 1, so for me that's between 0.1 and 10, somewhere in that range, I expect that the reaction will be about 50% complete. The last example we'll look at here, students were studying a reaction PCl3 and chlorine making PCl5. They've got a 4-liter flask with 0.560 atmospheres. So I'm anticipating this might be a, oops, I think there's a typo here, a Kp question, not a Kc. So I'm going to change that to Kp. If 15% of the chlorine reacted while the system reached equilibrium, what's the value of Kp at this temperature? There's no temperature actually mentioned in the question, so there would be no way to take a Kp and convert it to a Kc. So we're going to have to find the Kp value because we're using atmospheres in the question. So we'll write the equilibrium down again, so PCl3, and again these are all gases, so I'm just going to omit the phases to be lazy. Makes PCl5. These were placed in the flask. Now the volume here is kind of irrelevant, isn't it? Because these are atmospheres, these are pressures. We can fill in the ice table by putting in those initial pressures. You had 0.560 atmospheres of this guy. You had 0.400 atmospheres of chlorine, and it doesn't look like you placed any PCl5 in the reaction, in the container. So if 15% of the chlorine reacted, we can figure out the change for the chlorine. All I'm going to do is like a grade 7 or 8 math question, 15%, 15 over 100, of the original amount, 0.400. I could do some mental math. 10% of 0.4 is 0.04, so 5% is 0.02, and therefore 15% would be 0.06. And you can also grab a calculator to do that. So the chlorine must have lost 0.060 atmospheres, which is 15% of its starting amount. So now I can fill in the other changes. The PCl3 is also going to lose because it's on the same side as chlorine. The ratio is 1:1, so it loses the same amount. The PCl5 is on the other side of the equation, and so therefore it's going to gain, not decrease. And it's also going to gain because it started with 0, right? You can't decrease if you start with nothing. And the ratio is still 1:1, so it'll gain the same amount. Its coefficient was a 1, the other coefficients were 1s, so everything here loses and gains the same amount. So now at equilibrium, 0.56 take away 0.06, there's 0.5 atmospheres left of the PCl3. 0.4 minus 0.06, there's 0.340 atmospheres of the chlorine, and 0 plus 0.06 is 0.06 atmospheres of PCl5. Now we want to know Kp. We'll write the Kp expression, which is just the equilibrium expression using partial pressures instead of concentrations. So pressure of PCl5 over pressure of PCl3 times the pressure of Cl2. So equals 0.060 divided by 0.5 and divided by 0.340 also. So Kp, and we're always using atmospheres for pressure when you're finding a Kp value. Okay, that's important to remember. So 0.06 divided by 0.5 and divide by 0.34, we get Kp as 0.35 for this reaction. Alright, so there is a few relatively simple equilibrium problems, standard introductory problems in equilibrium. The questions will get a little bit more difficult. We'll be using some algebra in the ice tables in the next set of questions that we look at.